Okay, so I'm Amanda. I'm a graduate student from Purdue University, and we're working with the SNEWS team. So I'm just giving a little bit of an overview of what is SNEWS and what does a server sort of look like that we've been working on the past few months. So SNEWS is a supernova early warning system, and I'm just going to talk about how it kind of plugs into this multi-messenger astrophysics world that we're working in. So first, just a little overview of the core collapse supernova. We have a massive star that goes under fusion and all the elements start to burn. And then we get to an iron core and the core will start to collapse. Eventually mass will start to fall in and we get this sort of outward shock that forms. Out of this shock, neutrinos are able to escape. And then at some time later, we're able to see the electromagnetic photons that were first trapped in the shock, but then we have the shock breakout so we can see the photons. So the main takeaway from a core collapse supernova that we're trying to use for SNEWS is that neutrinos will come before the E&M signals from a supernova. So the time between the supernova neutrinos and the E&M signals ranges from a few minutes to a few days. So this plot is just showing different types of progenitor stars and how long it'll be between the supernova burst and when the shock breakout happens. So blue supergiants will have less amount of time between the supernova neutrinos and the E&M signals, where red supergiants have a bit more time. So we can use this to try and figure out what's the amount of time that we need to have between our signal sending out an alert and warning the rest of the multi-messenger community. So with supernova, we don't just get neutrinos and electromagnetic detections, but we also have gravitational waves. So all three of these together is what's going to make having a supernova go off sometime soon really, really interesting. This plot is just showing the luminosity as a function of time. So when the core collapse actually happens is in the middle of this plot. We see that there are some pre-supernova neutrinos that come out and they increase in luminosity as we get closer to the core collapse. And then after the core collapses, we see a lot more of the neutrinos that come out, gravitational waves, and then at some time a little bit later, the electromagnetic detection. So the main goal for SNEWS is to be able to provide the astronomy and the multi-messenger community a prompt alert indicating we saw supernova neutrinos. So be prepared. We expect a rate for core collapse supernovas in the Milky Way to be about 2 per century. So since they are pretty rare events, we need to be prepared when one does happen so we can collect all and do all this cool science with the supernova. So having SNEWS lets us do a couple of things. We have a variety of different neutrino experiments, and having them all together will give us the ability to triangulate on the sky where the supernova is going to happen, so we can tell the observatories this is where you should look on the sky for the supernova in a few minutes, hours, days. SNEWS will be a prompt and automated system so that we can quickly take the alerts from our neutrino experiments and give them out to the multi-messenger community. By seeing when the neutrinos arrive in the neutrino experiments, we can give a timing window for gravitational wave surges. And then this will also provide this early warning for the electromagnetic observatories to record the shock breakout. Previously, we've only recorded the end of the supernova, but if we can observe the shock breakout and everything, that'd be a really cool experience and project that everyone can be a part of. So SNEWS has quite a breadth of different neutrino experiments that are part of the collaboration. So we have sort of categorized them into 5 different types of detectors. We have water shrink-off detectors, scintillator detectors, neutrino and low background detectors, lead, and then liquid noble dark matter detectors. Each of these kinds of detectors are able to see a different type of neutrino flavor, and it also does different triangulation pointing and has different timing resolution. So putting all this information together will allow us to do to improve our sensitivity for giving information for our alerts in position and timing for the multi-messenger community. So currently we have SNEWS 1, which was developed in the 90s. It has, there's a handful of neutrino experiments that are a part of the network. And what it would do for the server currently is that we look for at least 2 experiments or more that say they think they saw supernova neutrinos within 10 seconds of each other. We make sure that these are located at separate facilities. The alarms are flagged as good rather than a test or a calibration mode, and that the experiments have a trigger rate that is below 1 per week. So we don't want it to be a noisy experiment contributing. And if all these requirements are passed, then we say we have a good alert, a gold alert, and we send that out to the astronomers, the public, and back to the neutrino experiments. And if these requirements aren't passed, it's just a silver alert where we alert the experiment saying something might have happened, let's do some more checks. What we're doing now is we're improving this from SNEWS 1.0 to 2.0, where we're working with the SCiMMA folks here and using Hopskotch to help with our communication between the experiments, the server, and the multi-messenger community. So the server is going to look a little bit different now, but it should have the basic sequence requirements of SNEWS 1. But we're also going to have more timing information, sorting these in time, hopefully looking for where is the peak of the neutrino in some sort of light curve, and also monitoring for signatures of pre-supernova neutrinos if they were to occur. So we hope to send out more often alerts to the multi-messenger networks and public email alerts, giving some a probability or a likelihood that this was a neutrino, a supernova event, so more frequent alerts than we had previously. So the server is sort of set up into two networks. We have our internal and external networks. The internal network is the small network of our neutrino experiments. This is 15, 20 or so experiments. It'll have a fast response time. So we see an alert, we do our analysis and check and see what's going on. The network itself will be static, but we're not going to really add many experiments in or out. Maybe we'll add one or take one away every couple of years or something. And then the information that is passed through the network will be closed or private so that as the experiments are sharing their data, other experiments can't learn what are all their events, but they can know if there was a supernova, whatever we would publish to the public. And then the external network, this is a large network for all the observational, all the observatories. This is the amateur astronomers. This would be a listen only network where we just send out alerts. It wouldn't happen as often as maybe the internal network receives messages. We would have a dynamic subscriber, so observatories and astronomers can sort of come and go. Hopefully they're coming more often than leaving the network. But this will be open and public, so once the data is released, then it can be used for everyone to kind of do what they want with the alert signal. For our internal experiment, this internal network, we have 3 different data sharing tiers that each experiment can sort of select which one they want to fall into. The alert tier is just if an experiment sees more events than their background is expected, they would send an alert to the server saying, hey, we think we saw something. This is essentially, the SNEWS 1.0 is tied into this alert tier. The significance tier would be the experiment sending more periodic information to the server, saying here's the significance of us detecting a supernova neutrino, maybe periodically, or if the significance changes rapidly, then they would send an alert to the system. And then the timing tier would encompass all of the other tiers, but would also send more timing information about each event they get in their specific neutrino channels. So SNEWS has tried to focus on sort of 4 or 5 different categories to improve from SNEWS 1.0 to SNEWS 2.0 and to prepare the community, the multi-messenger community for these signals. So the first one we want is promptness. We want to quickly analyze the supernova neutrino data, determine if we saw a signal and send out an alert. So this plot here is just showing the probability as a function of time from the supernova, and sort of the latest we would send an alert out is 10 to few minutes after the supernova signal, which is still a pretty fast turnaround time considering the amount of time we have between the supernova neutrinos and the E&M signals. So this is pretty good, but we're going to improve on this latency for SNEWS 2.0 configuration, hopefully getting it down to only a few seconds or a minute or so between the neutrino signal and sending out our alert. We want to have positive alerts. SNEWS 1.0 had a false positive rate of less than 1%. When the SNEWS 1.0 was first developed, the community was like, don't send us false alerts. We won't trust you in the future. But now today, the multi-messenger community is like, hey, give us all the alerts. We can handle all of them and worry about them ourselves. So we're going to send out more alerts more frequently. We'll have a likelihood to the alert saying the probability of it actually being from a supernova. And maybe we'll deliberately send out alerts that are most likely false so that we can sort of test the pipeline and see how the community responds to an alert being sent out. We will improve on our pointing so we can figure out where on the sky the neutrinos are coming from by looking at the time difference of these neutrino events from different detectors. This plot is just showing the one on the left is a sky map of the probability of the location on the sky given 2 neutrino experiments. This was from IceCube and SuperK. But if we add more experiments into our likelihood for pointing and triangulation, we can narrow this down to a smaller region on the sky. So the picture on the right is showing if we had 4 experiments combining their timing and pointing analysis so that we can get a better region on the sky to tell the observatories this is where you should look for the supernova, where the black dot is where the simulated supernova happened. So having a smaller region is obviously a lot better for telling the telescopes where to swivel. And then what we couldn't do previously with SNEWS 1.0, with SNEWS 2, we're going to look at pre-supernova neutrinos. These anti-electron neutrinos should come from the silicon burning in the core, and this should be detectable hours to days before the explosion. So if we see this increase in pre-supernova neutrinos, we can get an idea of when the core collapse is actually going to happen. And then we want to follow up on our alerts. We don't just want to send an alert out and say, see you later, we're done working with the astronomers, but we want to have a conversation. How did the alert help you? What did you do with the alert? But also update the alerts as we gather more information from the neutrino experiments. So maybe we send out a quick update as soon as we get some information from neutrino experiments, but while we're waiting for these other experiments, we can update the triangulation or the timing information that we have to update and give a further alert to the community. So this was the sort of timeline for developing this new server, the SNEWS 2.0 server. This summer, we started working on prototyping with SNEWS 1, putting the requirements into Hopskotch. This is what Bryce is going to demo in a few minutes. So now that we have a working prototype with SNEWS 1.0, requirements, all that into this Hopskotch server, we want to sort of map out what do we need to include now for SNEWS 2. So once we have all of them mapped out, we can start implementing these new protocols in the summer of 2021 into the Hopskotch client that we currently have. So in summary, a core collapse supernova will produce a neutrino signal before the E&M signal. So we want to have this early warning to prepare everybody. SNEWS 2 will have a broader network than before. We have more than 15 neutrino experiments that are including dark matter detectors. So we can do a lot of improved triangulation and pointing with even more experiments. And then overall with SNEWS, we will produce more frequent alerts, extend our distance reach, include pointing and triangulation, follow up with information, and then conduct pre-supernova analyses. I think that's all I have. So is there any questions? We're going to switch over to Bryce now. So while he starts sharing his screen, I can answer questions if there are any.
Okay, if there are no questions, I'll go ahead and start. Can everyone see my screen and hear me?
Yeah.
Great. Okay. So what I'll be going through is just the rundown of what we prototyped over the past few months to get SNEWS 2.0 revamped using Hopskotch. And just briefly, this is kind of the product of different people's work. Initially, a lot of the development was by Skylar Zhu, working to get the groundwork of the SNEWS 2.0 app ready. And then the past 6 weeks, SCiMMA and SNEWS developers have been collaborating to improve that app and get it going to the prototype that it's at right now. And so without further ado, we'll go into how we've kind of met the SNEWS 2.0 needs with the prototype so far. So again, as a reminder, the basic need is to have some kind of messaging and server layers that will allow neutrino experiments to send the messages out to a server where they can be processed and decided upon to see if there's any coincidence between the messages or detectors, and to get ready to send out an alert to the various networks and multi-messenger communities. And so to get these different components, we need kind of 3 main features. Initially, we need just the basic function that determines if there is an alert by looking at messages. But to do that, we'll need to be doing message interfacing for the different detectors and clients so that we can even have the messages being passed. But then that'll also require the server infrastructure to coordinate all those messages being sent. And so with the SNEWS 2.0, we've done the first 2 with the SNEWS app. And we'll talk about how we met the server infrastructure later. So with the SNEWS prototype app, what we have is a method to receive messages, parse them, and then send out alerts. And so the quick architecture rundown is the app has a storage component, which is where the messages are cached locally for the client, which allows the database to be portable depending on if the requirements change for future iterations after the prototype, or if we want to implement server-side a database instead of client. And so it's a basic kind of storage layer. On top of that, we have the decider, which is what actually skims through the messages, reads them, and applies its parsing logic to determine if there's a coincidence between messages. And right now, that logic just involves kind of basic co-occurrence within a time window for different events, and if the events are coming from different detectors. But that's going to be extended to have more interesting astrophysics like sky maps and pointing later. And then on top of all this is the model, which is what instantiates the decider and starts connecting it to all the message plumbing going on. And what the model then does is listen to the decider and wait to see if a message comes in that triggers a coincidence, and then the model will get ready and send an alert out to the community. And it does the message interfacing by extending SCiMMA's Hop client app and using its streaming API to connect with the Hopskotch servers with authentication and configuration. And so that takes care of the first 2 needs, to decide and parse the messages and start sending out messages. And then the last component is, of course, the server infrastructure, which is where the Hopskotch Kafka broker servers come in. And so what this lets us do is see everything in kind of picture where we have the individual app elements connecting and talking to the different server elements. And for the purposes of the prototype, we're looking at the internal network, so not worrying about the external astronomer community yet. We're just looking at the internal message plumbing to make sure everything's working correctly. So at the most basic level, we have the SNEWS app in the center waiting for the detectors to start sending messages to topic 1. The SNEWS app is listening to that topic and checking those messages that come in and getting ready to send out an alert if it meets its parsing logic. As soon as that happens, the decider and model then send off that alert to topic 2. Again, this is internal, but topic 2 is the message stream that the SNEWS detectors are subscribed to, so they're going to get that alert. And so the message streams for the topics are not handled by the SNEWS app, but that's how the Hopskotch server comes in and provides the service where the messages can be sent to and then read from. And so these 4 elements are what constitute the SNEWS 2.0 prototype right now. And there's, of course, documentation and code bases for all this, and I'll give links to those at the end of the talk. But the kind of good way to see how everything works together is to do the demo. And so for this, I'll go ahead and switch over to terminal view and just show what the setup looks like with the different components talking to each other. So what we have, we're going to have 3 detectors here. We have one detector, which is going to be a triggering detector in Ohio. The different regions are served through AWS, so they're actually, the servers are actually kind of located in the general region. So we have one triggering detector in Ohio. We have one out in Australia. Then we have another local one, which is what's going to be listening to alerts as they come in. So we have the 2 triggering detectors subscribed and connected to topic 1. And then we have, of course, the follow-up detector listening on topic 2. And what we're going to have on top of that, we want to be listening to the messages as they come in from the detectors to check the latency. So we're going to have a latency checker in the bottom left, and we'll go ahead and start that up, and then it'll be listening to messages as they come in. We're also going to want to monitor the messages as they come in themselves to read the message content, and I'll do that locally just on my machine. So we'll go ahead and start that up as well. And then lastly, we're going to need the detector for follow-up listening on the proper topic. So we'll go ahead and connect it using the Hop client. And so right now there are no messages flowing, so we don't see any updates coming through, but we're going to change that pretty soon. So we're going to go ahead and have this one detector in Ohio start sending in heartbeat messages. So these are just going to be routine messages coming in. And as soon as we start sending these, we'll see some activity in the bottom where we have latencies come in. These are the time from the detector sending the message to it being received locally. And so we're getting a bunch of messages come in, and the latencies from Ohio are around about 100 to 200 milliseconds on average. And you see all the message content coming in the bottom right, again, locally. No alerts are being sent, so this detector up here is just waiting but not getting anything to topic 2. So we'll go ahead and have that. We'll send in a few messages from the Australia detector just to show that the latency does differ a little bit. And yeah, sure enough, we have 200, 300 millisecond latency, so it's a little bit slower. But the messages still come in, and even though it's a different detector, these are still all heartbeats, so we're not getting any actual neutrino detection, so we still don't have any alerts. But it's about time we change that. So let's go ahead and start sending out some alerts. And so we'll do that by, again, talking to the mock observatories in Ohio and Australia, and we're going to start having them send out real alerts. And so as soon as we do that, we just start seeing messages come in up here. And this is just the kind of proof of concept that, okay, what's happening is we have the detectors sending in messages to topic 1. That's good. A lot of those were just heartbeats, so we weren't getting any alerts. But then as soon as we turn the switch on and say, okay, we're observing something, we're getting neutrinos, the decider was waiting the entire time, and it applied its logic and said, okay, we're getting some coincidences now. And then we're going to send out alerts to topic 2. Then that third follow-up detector is getting those messages, so it's ready to do any kind of follow-up it needs to afterwards. And of course, as soon as we stop the streams, we won't be getting any new messages. But that just shows that all of the plumbing, even though it's distributed where we have these different regions, different servers, local servers, they're all playing nicely together because of the plumbing. with SNEWS app and the Hopskotch server all working as part together. So that more or less concludes that part of the demo. Again, the architecture with the different components is what we just saw. And other than that, we just have the different resources. So there are some more overview notes if you're interested, and also some tutorials to do what we just saw today, but fully locally. So you don't need Hopskotch credentials. You can just do everything with local servers and local message passing to kind of replicate that same plumbing between mock detectors and mock receivers. There's also tutorials for the getting real detectors hooked up into the Hopskotch network with proper authentication and accounts, and as well as the code base and docs for the different components, the SNEWS and Hop client. Other than that, I'll wrap up there and take any questions.